Hello everyone again and welcome to the DMSI YouTube channel, and it's truly a pleasure to actually have you all in this particular space. And in this particular video, we're going to be exploring an example of our past video, which involves determining the collision flux and deriving that particular equation, which is what you see in this particular screen right here. So we have our pressure is over all square root of 2 pi m, which is the mass, multiplied by the Boltzmann's constant, multiplied by the temperature, and we derived this equation from various interesting themes on our previous video. First, determining the number density, and then looking at how you can incorporate the specific relative mean speed to becoming the mean speed, which is what we have right here, which turns out to be 1/4 or quarters of the mean speed. And so therefore, this is then introduced in our integration, which accounts for the variation or distribution of velocities towards a specific wall barrier or space wall that a particular particle is hitting against at a particular time interval. And so we are now going to be able to use these parts of the derivation process or deriving process to perform this particular question. Looking at this question here, it says that a solid surface with dimensions of 3.5 millimeters by 4 centimeters is exposed to helium gas at that particular pressure of 111 at a specific temperature, which is 1500. And now you're asked, how many collisions do helium atoms make with the surface at that particular time? So in this part here, let's have a little diagram to visualize what is going on in this particular question. And so in the diagram, we are assuming that we have a surface that is solid in nature, and we have the dimensions of this surface, and the dimensions of the surface is, in this case, we have the measurement of the width to be 3.5, and this is units to be millimeters, and while this is by 4.0 centimeters. And this measurement here for the area is going to be making the units to be equal, not only in terms of the dimensions but also the area. Therefore, our area will be in meters squared when you determine that particular combination. So this particular wall is experiencing some form of pressure by particles that are heading towards it, and the specific particle, when we actually release them into a particular space like this, is called helium. And so helium, which is pretty much a uni atom in this case, is going to be heading towards the wall, and the velocity, which is represented as v at x, which in this case, putting our coordinates, will be able to assign the unit dimensions direction to be in terms of the x. Therefore, from the time it's released to when it hits, we actually are going to assign it at changes time, and therefore we'll be able to determine our distance, which we did on our previous video. So our change in time is measured in seconds, and it is 10 seconds in this particular question. So these are the necessary information, and other information based on the givens includes the following. We have our givens, which is, first, we are given the area indirectly of the solid surface, and to determine that, first we need to convert our units. So in this case, we are getting 3.5 millimeters by 4.0 centimeters. And so to go from millimeters to meter, we are going to be getting our number, in this case, for 3.5 to become 3.5 times 10 to the -3. This is multiplied by, for centimeters to meter, it will be in this case 4.0 times 10 to the negative 2 meters. So once you have this, our answer in this case will be around 14.0 times 10 to the negative 5 meter squared. And this is actually our area for this particular surface that our particles will be colliding at. Now, the next variable that we're given in the question is the pressure, and the pressure here is, according to the standard unit, in this case is pascals 111, and then we have our other variable, which is temperature, determined or given to be 1500 kelvins, which is also one of the units that is standard for this overall equation. And then our change in time is in this case given to be 10 seconds. And next is the molecular or the atomic weight of helium. So in this case here, which we are going to determine is that, hey, we need to convert it from grams per mole to kilograms per mole. And looking at the periodic table, we notice that it is around 4.01. And so converting it to kilograms per mole, we actually multiply this by 10 to the negative 3 kilograms per mole. So once you have this, there are other standard units that we're going to come across, which includes the following. We're going to be given the gas constant, or we're going to be using it, which is 8.314, in this case, joules per mole times kelvins. And then the other one is our Boltzmann's constant, which is around 1.38 times 10 to the negative 23 joules per kelvins. So once you have all these variables assigned, we are now going to go into what is required. Now, the required here in this question is to be able to determine what the number of collisions that will be exhibited in this particular state. So the number of collisions is going to be determined, and to determine that, we need to determine what the Z is. Now, there are two types of Z. One has a subscript, which has an M, and the other Z, which is a small letter, actually is expressed as, in this case, the collision frequency, which tells us the number of particles that will be collided by one particle at a particular time period. And so, in this part, we need to then look at our analysis and figure out how to rearrange a specific equation, and from there be able to have the subject of the formula to be in terms of the collision frequency. So in this part, we know that the collision flux, which is what we derived from our previous video, is expressed as huge Z with subscript M, and this is equal to the number density multiplied by 1/4 of the mean speed. And we know that this is also equal to the collision frequency, or divided by the area multiplied by our time interval. And so once we have this taken care of, we know that since this is in this case going to be expressed as equation 1, we are going to put our equation for the mean speed, which is in this case square root of 8 RT over pi multiplied by the molecular weight. We're going to put this in equation 1. Therefore, once you put this in equation 1, we'll be able to re-express our equation, which is what we have here, in terms of these particular variables. Once we have this taken care of, our next step here is to assign this to be equation 2, and we're going to put another equation where we're going to change our number density now to a form that will show the pressure relationship with temperature. And this is actually, as the denominator, will be introducing our Boltzmann's constant. Therefore, putting this in equation 2, once we have this new equation derived, we're going to use this equation to determine our specific collision frequency. So we're going to solve for Z. And so to solve for Z, we will have to do what? Multiply both sides by a change in time, and therefore our new equation, which is now in terms of Z, is equal to, once we have this equation, we'll be able to solve for our Z by putting all our givens in this particular part in this particular expression right here. And so therefore for our Z, so once we have this taken care of, we are going to evaluate the unit and also evaluate the constants in all these expressions. So focusing here on the unit, we know that our meter squared is going to cancel out our meter squared. We know that in this part here, our Newton will cancel our Newton. We know that our kelvins will cancel our kelvins. And on this other side, take note that we also are missing one thing, which is our 1/4, which is what we have right here. So don't forget this 1/4. We'll need that very soon, which is what I'm going to put in between the two brackets as the multiplication process occurs. And then inside our square root, we have our grams, definitely cancelling out our grams. We have our moles, cancelling out our moles. We have our kelvins, cancelling out our kelvins. And what we're left with in our unit inside the square root is meter squared over second squared. Therefore, in our final step, take note that this here is 5. I made a mistake. It's meant to be 5, not 4. So 10 to the power of 5 times 10 to the power of 1 is equal to 10 to the power of -4. Therefore, in this case, we have our units to be here in seconds, which is what is left. And then we'll multiply all this by 1/4. And then what we have is our value to be 1.34057 times 10 to the 21. And our unit is in meter -1. And the other one now inside this particular square root is we have, and take note here that our unit is in meter squared over second squared. So once you have this expressed as that, we're going to further evaluate the square root, and then from there we'll be able to analyze everything at the end. So in this part here, by re-evaluating this, we have, and then our square root, and we have our meter squared to become meter over our second squared to be seconds. And so next is evaluating our units. Seconds cancels out our seconds, our meters cancels out our meters, and what we are left now is our Z value. Once you multiply the constant, is in this case the collision frequency, which is in this case the number of collisions that helium will experience against the wall in 10 seconds at that particular pressure, which is given the question, and temperature to be equal to 5.2816 times 10 to the power of 21. That is that many collisions that is going to be made during this particular process dealing with helium atoms in that particular space. So that is really a huge amount of particles in just 10 seconds that will experience collision, and therefore causing an increase in pressure against the surface that is the solid surface in this particular question. So I hope you found this particular activity interesting in terms of not only getting the right formula that will be required for you to fit all the required variables, but also to be able to watch out for the units and also be able to arrange your solution in an orderly way in order for you to get to your final answer in this particular case right here. So that's about it for this video. I hope you have found this really informative. Please hit a comment down below. Let me hear your thoughts. By that way, I can talk to you soon. Stay smart as always and believe in yourselves.